Hello students, in this class we will discuss about the character feedback biasing. Okay, character feedback biasing. So in the last sessions we will already discussed about the that is fixed biasing, and second one is emitter biasing. Next, emitter biasing. These two are completed already. So next biasing is the character feedback biasing. So look at here, we have a transistor, that is emitter, base, collector are the three terminals. Observe here, from the collector we are using a feedback resistor, that is RB, and it is connected to the base. So by this concept it is called as the collector feedback biasing until remaining circuit is the same. So collector have the resistor, feedback resistor RC, and emitter is directly applied to the ground. Okay, so here now we will find, our intention is to find out the Q point. What is Q point? Q point is nothing but VCE and IC, character output voltage and the character voltage. Here, in order to get this, first we need to find out the first to find out the character current IC, we need to find out the base current. This is the procedure first. So how we will get the base current? So look at here, this is the character current flowing from this coin point, and this is the base current. This will reach the emitter current. This will reach the emitter current. Okay, here observe here, first we will write the loop equation for the input loop. So this is the input loop, just observe here, just apply the loop equation for this input loop. This is the loop equation. So if you write the loop equation, what happen? If you write the loop equation, this is not character current actually, this is the character current. This point is the collector current. Which current is entering into the collector region is nothing but the collector current. So this is the, take it, this is the current I. Then the combination of the current is entering into the base is the this current, and current entering into the collector is known as the collector current. Then this collector total current I is nothing but the base current plus the collector current. Okay, so we will find out, in order to find out the collector current, first we need to find out the base current. So for that purpose, just I need to writing a loop equation from the base region. So this is the loop equation. This loop equation is simply VCC minus drop across this point, drop across I. I means the combination of base current plus character current, base current plus character current, and resistor, and minus base drop across the base minus VBE is equals to 0. This is we know that this is the loop equation from the supply to the emitter from the base region. But we already know that is collector current equal to beta times of base current. Just substitute here VCC base current plus beta times of base current into RC equal to IB RB minus VBE is equals to 0. So from this we can common the base current. So just the common the base current here. Base current is 1 plus beta RC is the one thing, and what is remaining? Remaining is the RB. Remaining is the RB. If you come on the minus, this is the RB. And remaining part is VCC minus VB. So from this directly I can write the base current. The base current equal to here. I am writing directly base current. Base current go outside become plus, and I will write direct equation VCC minus VBE by 1 plus beta into RC plus RB. RC plus RB. Okay. So this is the base current value. Base current value. But what is the relation between collector current and base current? You know that the collector current is nothing but beta times of base current. So beta times of base current means VCC minus VBE by 1 plus beta in RC plus RB. Okay, this is the collector current equation. So this is the collector current equation. So this is the collector current or operating point. Collector current are the operating point. And we have to find out the next thing, that is the output voltage. So from this equation directly we will apply the loop equation for this region. So for this region directly you will apply the loop equation. Yes. So here just apply the loop equation. I am directly writing the equation. That is so applying the loop equation we will get. So otherwise you can understand like this. Yeah. So better to take outside. So here so I am writing the loop equation for here. So now if you apply the loop equation here, this is the VCC, drop across this and drop across this point. So from that I can write directly, this is the VCC minus drop across this point is nothing but I into RC minus drop across output VC equal to 0. So but you know that the total current will be equal to the combination of current base current plus the collector current. So from this you can write VCC equal to IB plus IC equal to RC minus VC equals to 0. This is base current plus collector current. Base current plus collector current. So from this I can write the output voltage VC equal to in the form of VCC IB plus IC into RC. This is the output voltage. This is the output voltage. This is the output voltage. Okay. So this is the output voltage and this is the output current. So you will get the 2 points now. So now we need to do what are the advantages and the disadvantages by doing this thing. So we are getting two things. So what are the advantages and disadvantages we have to think. So for this purpose, first look at the advantages. So generally you know that the advantages are we have some advantages. Those are first point is, this is against the variation of temperature. So already same as emitter biasing, against the variation of temperature. So it will control the temperature. And the second point is same, again is the variation of the, we have a new point, that is the VCC. It will control the VCC also. And the third point is again is the variation of the amplification factor beta. So beta can be varied, but you know the beta current, you know that this is the collector current, that's why it can vary the beta. How it is vary the beta? Whenever it is possible, 1 plus beta RC is very greater than RB. So that is the same problem here. So again, the problem with, we have a disadvantage, that is to maintain IC control. What is the condition here? Same as emitter resistance, 1 plus beta RC must be more than the RB. More than the RB. So same problem we will face here. Same problem we will face here. Same as. So this is the disadvantage. Okay. So whatever the problems occur, once again we will recollect the disadvantages. In order to do that, this is the problem. This is not possible generally. What is the first problem here? The first problem is beta is independent. We don't know the beta value. This is the first problem. And what is the second problem? RC must be very high. RC must be very high. Whenever RC is very high, what happens? Supply biasing also very high. So due to that, cost of the transistor will be increases. Cost of the transistor will be increases. And the second point, RB must be very low. So what is the problem with RB must be very low? So then base and collector junction resistance will be decreases. That means reverse bias must be reduced. So due to that, the same problem occurred. It is not possible. So these are the generally the problems in the corrector feedback biasing. So everything has some advantages and some disadvantages. Advantages as well as the disadvantages. Okay. Here the problem is given related to the collector feedback bias method. Here determine the operating point. So this is the network shown in the network. First, before that, just note down the given values. First, the supply voltage VCC, you know that the 20 volts, and it is nothing but the RC collector resistance, that is RC. We can take 1 kilo ohm, and this resistor is connected to base, that's why it is the RB. So here RB is 100 kilo ohm, and these are the connections he given, and he mentioned the beta also, current amplification factor, that is the 100. So he asked to find out the operating point. So what is operating point? Operating point is nothing but the Q point. Those are operating voltage and the current. The operating voltage of the output is VCE and the output current is the collector current. So for that purpose, so in order to get that, first you need to apply the base loop equation. So first base loop equation you need to apply. So this is, I can directly apply the loop equation here. From this we have the drop VCC is there. So VCC minus drop across this point. So this is the current flow in the branch, and this is the total current come outside, and this is the collector current. This is not collector current, this is the I current. This point is the collector current. So that's why this current I can be write it as the combination of base current plus the collector current. So VCC drop across this point. Drop across this point means directly I am writing IB plus IC into 1K. Next, drop across this. This is the drop IB into 100K minus drop across VB. VB means the 0.7, that is the 0. So you know that already IC value is beta into IB. Directly I am substituting beta into IB. So I will write beta outside, that is beta value I can write like this: beta equal to 1 plus beta plus 1 plus beta into 1K is there, 1 plus beta is there, 1K is there, right? And we have IB into 100K equal VCC minus 0.7. VCC minus 0.7. This is equal, this is nothing but this. So from this I will write the base current. That base current equal to VCC minus 0.7 by 1 plus beta plus 100K. 1 plus beta into 100K. Here you know that what is VCC? VCC is 20 minus 0.7. Here 1 plus beta, here forgot you 1K, I think. This is, here is the 1K is there. You forgot again 1K. Right. Here we have beta value, you know that 100. So 1K into 1 plus beta means 100 plus 100K. So by doing the simplification you will get the base current equals to beta equals to directly we will write beta value equal to 96.4 micro amperes. So this is the base current. What we have to find out, but the collector current we need to find out. So collector current equal to beta into base current. So again beta, you know that beta is given 100. This is 96.4 microamperes. So by using this we will get the collector current is 96.4 into 10 power minus 4 amperes, because micro means 10 power minus 6, right? Here in order to find out the, so we already find out the operating current, collector current IC, but we need to find out the VCE. For that purpose, what is VCE there? So in order to find out the VCE, look at VCE. So we have to apply the loop equation for this output loop. So for this I am applying this loop equation. So directly I am applying the loop equation. You will check that loop equation later. So here the loop equation is, I can write directly loop equation, that is 20 minus IC plus IB into 1K minus VCE is equals to 0. So supplying all the currents, 20 minus collector current equal to 96.4 into 10 power minus 4 plus base current equal to 96.4 into micro means 10 power minus 6 into 1K will minus VCE is equals to 0. By doing the simplification, you will get the output voltage VCE equal to approximate 10.3 volts. So collector drop is 10.3 volts. We see we have some drop, that is 10.3 volts. Okay, so finally we will get the operating point or Q point value is 10.3 comma 96.4 microamperes. Sorry, not microamperes, 96.4 into 10 power minus 4, 10 power minus 4 amperes. So this is the Q point or operating point of the given problem. So here we asked to find out the operating point. Okay, this is the procedure to do any problem regarding the collector biasing configuration. Okay, I think all of you understand this session. Thank you.